Assalamualaikum warahmatullahi wabarakatuh and greetings everyone. Welcome to my final year project presentation. My name is Putri Nurfarah Shufah binti Ruslan, a final year student in Bachelor of Science Honours Chemistry Forensic Analysis. Today, I am delighted to present my thesis research on the photophysical properties of sulfoindocyanine in deep eutectic solvents and molecular solvents. This is the outline of my presentation, and without further ado, let's start with the introduction section. To begin, organic molecular solvents are crucial in industrial and laboratory settings for their ability to dissolve various solutes in processes like chemical reactions and material synthesis. However, their widespread use raises environmental and health concerns due to volatile organic compound emissions, contributing to air pollution and human health risks. To address these issues, safer and more sustainable alternatives are actively being sought. The green solvents such as ionic liquids, supercritical fluids, and deep eutectic solvents are explored with the focus to offer reduced toxicity and environmental impact while maintaining solvent efficiency. Deep eutectic solvents, or DES, are gaining attention as eco-friendly alternatives to conventional solvents due to their low toxicity, biodegradability, and unique physical-chemical properties. Composed of hydrogen bond acceptor HBA and a hydrogen bond donor HBD, DES form eutectic mixtures with lower melting points than their individual components. They find application in catalysis, extraction, and electrochemistry. Despite their promises, DES face challenges such as high viscosity, which can affect mass transfer and flow behavior in industrial applications. One of the primary challenges is the high viscosity of DES, which can hinder their use in industrial processes. High viscosity can affect mass transfer rates and make handling and processing more difficult. Furthermore, there is a limited understanding of the local viscosity within DES. This lack of understanding can impede the optimization and broader adoption of DES in various applications. This study focuses on molecular level solvent viscosity analysis using fluorescent probes, offering insights into local viscosity. Accurate viscosity and polarity measurements are crucial for optimizing chemical reactions. Cy3 dye, which also a fluorescent molecular rotor, is used to explore solvent viscosity effects on dye photophysical properties in both molecular and green solvents. Understanding this effect can enhance chemical process efficiency and facilitate the development of improved solvents for diverse applications. The objectives of this research are threefold. The first one is to prepare and characterize the physical and chemical properties of deep eutectic solvents of different viscosity and polarity. Next, to measure fluorescent signal of Cy3 in DES and molecular solvents. And finally, to correlate the fluorescent signal to the viscosity and polarity of the solvents using the Forster-Hofmann's equation. Future review focuses on sulfoindocyanine dye or Cy3 dye used in this study. The use of 3,3-diethylthiacarbocyanine iodide, which also a part of Cy3 group, features a polymethylene bridge with alternating single and double bonds between nitrogen-containing rings. These are crucial for its fluorescent and molecular rotor properties. Cy3's fluorescent sensitivity to environmental viscosity makes it a valuable tool for measuring solvent properties. Beyond this study, Cy3 finds application in DNA and RNA labeling for fish experiments, protein tracking in dynamic cellular studies, and targeted microscopy for disease imaging, including cancer. The research methodology comprises several key steps, each aimed at achieving the objectives of the study. The methodology starts with synthesizing the DES by mixing a hydrogen bond acceptor and a hydrogen bond donor at specific molar ratios. The mixture is then stirred and heated to form a colorless liquid, which is dried and stored in a desiccator for further use. Next, the DES were characterized using nuclear magnetic resonance (NMR) and Fourier transform infrared spectroscopy (FTIR). These techniques provide information on the molecular structure and interactions within the DES. The physical properties of DES, which is the solvent's viscosity, were characterized using a rheometer. On to the method that accomplishes the second and third objective of this study, the fluorescent measurements and correlation analysis. The maximum absorption of each solvent in this study was first determined using the UV spectrophotometer before the fluorescent signals of Cy3 dye in different solvents are measured using a fluorescent spectrophotometer. The fluorescence data was then correlated with the viscosity and polarity of the solvents using the Forster-Hofmann equation. This analysis helps to understand the relationship between solvent properties and fluorescence intensity. The spectra comparisons in both the FTIR and NMR analysis illustrate the differences between the pure components and the DES, emphasizing the formation of new interactions were observed. The central image shows the chemical structures of each prepared DES, highlighting their interactions. Starting with the FTIR analysis on the right, the spectra show significant interactions between the components of the DES. For this DES of choline chloride malonic acid, a shift was observed at the C double bond O stretching peak from wavelength 1738 in pure malonic acid to 1716 in the DES produced, indicating interaction. Similarly, the OH stretching peaks shift from 3436 in pure choline chloride to 3336 in the DES, confirming interactions between hydrogen bond acceptors and donors. Moving to the NMR analysis on the left, the peak assignments and chemical shifts provide detailed insights into molecular environment of the prepared DES. At 4.72 ppm, labeled A, was classed as the CH2 group from choline chloride. The 3.40 ppm peak, labeled D, corresponds to the OH group from malonic acid. At 3.08 ppm, labeled F, we find the CH3 group from choline chloride. And lastly, the 2.02 ppm peak, labeled G, corresponds to the CH2 group from malonic acid. Next is on the chemical characterization for the prepared choline chloride glycerol. FTIR analysis on the right, the spectra shows significant interactions between the components of the DES. A shift was observed in the C double bond O stretching peak from 1086 in pure choline chloride to 1040 in the DES, indicating interaction. Similarly to OH stretching peak shifts from 3414 in pure choline chloride to 3307 in the DES, confirming interactions between hydrogen bond acceptors and donor. On to the NMR analysis on the left, the peak assignments and chemical shifts provide detailed insight into the molecular environment of our DES. At 4.70 ppm, label A shows the CH2 group from choline chloride. The 3.97 ppm peak, label B, corresponds to the CH2 group from glycerol. At 3.68 ppm, label C, we find the CH2 group from glycerol. Lastly, the 3.11 ppm peak, label F, corresponds to the CH3 group from the choline chloride. As for the prepared choline chloride urea, a shifting was observed in the C double bond O stretching peak from 1641 in pure choline chloride to 1662 in the DES, indicating interaction. Similarly to NH stretching peaks shift from 3434 in pure choline chloride to 3320 in the DES, and from 3461 in pure urea to 3336 in the DES, confirming interaction between hydrogen bond acceptors and donors. Moving to the NMR analysis on the left, at 4.70 ppm, label A, we see the CH2 group from choline chloride. The 3.99 pm peak, label B, corresponds to the OH group from choline chloride. At 3.45 ppm, label C, we find the CH2 group from choline chloride. And lastly, the 3.14 ppm peak, label D, corresponds to the CH3 group from choline chloride. For choline chloride 1,4-butanediol, shifting was observed in the CH bending peak from 944 in pure 1,4-butanediol to 950 in the DES, indicating interaction. Similarly, the OH stretching peaks shift from 3,292 in pure 1,4-butanediol to 3,304 in the DES, confirming interactions between hydrogen bond acceptors and donors. Moving to the NMR analysis on the left, at 4.70 ppm, labeled A, we see the OH group from 1,4-butanediol. The 3.94 ppm peak, labeled B, corresponds to CH2 group from 1,4-butanediol. At 3.11 pm, labeled D, we find the CH2 group from choline chloride. And lastly, the 1.49 ppm, labeled F, corresponds to the CH3 group from choline chloride. The last prepared DES is the choline chloride ethylene glycol. A shifting was observed in the CO stretching peak from 1034 in pure ethylene glycol to 1040 in the DES, indicating interaction. Similarly, the OH stretching peaks shift from 3,438 in pure choline chloride to 3,292 in the DES, confirming interactions between hydrogen bond acceptors and donors. Moving to the NMR analysis on the left, at 4.70 ppm, labeled A, we see the OH group from ethylene glycol. The 3.97 ppm peak, labeled B, corresponds to the CH2 group from ethylene glycol. At 3.57 ppm, labeled C, we find the CH2 group from choline chloride. And lastly, the 3.12 ppm peak, labeled E, correspond to the CH3 group from choline chloride. These chemical shifts and peak assignments help us understand the structural and electronic changes due to the formation of the DES. The physical characteristics of prepared DES, which is in this study, is the solvent's viscosity, were measured using a rheometer instrument. The shear rate was set at 1/250 per second and the reading was taken at 20 points. The result obtained from this instrument confirmed the viscosity of each DES prepared, as well as proving the Newtonian behavior of the DES studied. It is said so because all of them have a constant viscosity regardless of the applied shear rate or shear strength. After the synthesis and characterization processes, the fluorescent measurements of molecular solvents and prepared DES were carried out. The UV spectrophotometer was first used to find out the maximum absorption of Psi3 dye in each molecular solvents and prepared DES. Having different reported viscosity and dielectric constant value, the maximum absorption of each molecular solvents were taken and tabulated in descending viscosity value and also in the order of the most polar to the least polar solvent. The data does not show any trend to prove that the maximum absorption of Psi3 dye in molecular solvents are sensitive to neither viscosity nor polarity. Once the maximum absorptions of Psi3 in all solvents were confirmed, the value was then used to set up the wavelength of excitation and emission on the fluorescent spectrophotometer. The fluorescent emission maximum intensity was tabulated in once again the order of descending viscosity as well as a descending dielectric constant value for polarity. The fluorescent emission intensity of Psi3 in each solvent was then correlated with the viscosity and polarity value of each molecular solvent. While the fluorescent emission intensity still does not show any trend with the polarity value, the fluorescent emission intensity value increases with the viscosity of the molecular solvent. This shows that Psi3 dye is sensitive to the viscosity of the environment, and this result is parallel to the previous studies that has been done using the very same dye, which stated that the fluorescent intensity of Psi3 increases with the viscosity of the environment. The fluorescent measurement process was then continued with the 5 prepared DES. This slide is on the maximum absorption value for the prepared DES that was tabulated only from the most viscous to the least viscous DES, as the polarity of the prepared DES were kept constant. The recorded maximum absorption of Psi3 shows that the viscosity of the solvents does not affect the maximum absorption of Psi3 in each eutectic solvents. As previously, the maximum absorption value of Psi3 dye in each DES was then used to set up the wavelength of excitation and emission on the fluorescent spectrophotometer. The fluorescent emission maximum intensity was then tabulated in the order of descending viscosity. The fluorescent emission intensity of Psi3 in each DES was then correlated with the viscosity of each DES. The fluorescent emission intensity value increases with the viscosity of the DES. This once again shows that Psi3 dye is sensitive to the viscosity of the environment. This finding aligns with prior research using the same dye, which has shown that the fluorescent intensity of Psi3 rises in tandem with the viscosity of its surrounding environment or solvents. All in all, 5 deep eutectic solvents were prepared and characterized using FTIR, NMR, and rheometer. FTIR spectra showed interaction between hydrogen bond acceptors and donors through shifts in functional groups. Psi3 fluorescent, typically insensitive to molecular solvent polarity, was notably sensitive to solvent's viscosity. Higher viscosity correlated with increased fluorescent intensity. This highlights Psi3's potential as a viscosity probe in DES and similar systems. Future research could include exploring alternative DES types to enhance fluorescent performance, conducting comparative studies with dyes like indocyanine green, body P, and DCVJ, and investigating additional fluorescent parameters such as quantum yield and lifetime. Additionally, studying alternative green solvents like ionic liquids and supercritical fluids could also expand the scope of green solvent research. Displayed is the list of references that I have cited throughout this presentation. At last, I really hope you find this presentation insightful, and thank you for your time and attention.